So today we're going to be talking about work and work energy principle. Firstly, what you need to know is energy transferred by force is the work done. So let's look at this example on top here. There is an object, we apply the force on it, which causes it to displace a length d by that force. So let's put it in mathematical formula. So mathematical formula, math formula for work done. So work done equals to force times displacement times cosine theta. So that's the formula where W is the energy transferred by force, energy transferred, where F is the size of force, D is the displacement, and cosine theta is the angle between the force and the displacement. So this is theta here. So now we're going to be talking about the units. So force is in newtons, distance is in meters. So we know that Newton meters is joules. So that's our unit. So let me write the formula again for you guys. So to better illustrate it again, W equals to force times distance times cosine theta. So if force and displacement are in same direction, then work done is positive. If force and displacement are in opposite direction, then work done is negative. So what happens if it doesn't displace? If it doesn't displace, if there is no displacement, then the work done is 0. So we understand that by looking at the formula here. So if there's no displacement, then that's 0, then work done is 0, which is kind of a very simple illustration there. So now let's assume you have an object with a lot of forces on it. Let's say F1, F2, F3, Fn. And let's assume we're trying to find the work done for all of those forces. So a simple way you could do it is like you could say work net equals to work 1 plus work 2 plus work 3 plus work n. You can consider this as a simple, but it will take you a lot of time. So for a shortcut, so let me write a shortcut here. You could do is you could find work net in terms of velocity. So work net equals to force net times d times cosine theta. Let's assume all of these forces are in the same parallel to the axis, then cosine theta equals 0, then all of this equals to 1. All of this equals to 1 if cosine theta equals to 0. So then work net equals to force net times D. So by first year kinematics, we learned that V squared, V final squared equals to V initial squared plus 2AD. So we have this from first year kinematics in terms of linear motion. So this is for linear, rectilinear motion, linear motion. So we can say that work net equals to force. Force can be broken down into its components. So mass times acceleration times D. For you to use the linear rectilinear motion, you have to assume acceleration is constant. So it must be a constant deceleration or acceleration. So in the end result, it won't matter. But for right now, we will assume acceleration is constant. So that our math looks easier and much easier to understand. So work net equals to, let's simplify this formula. So V final squared here minus V initial squared over 2 equals to acceleration times displacement. So work net equals to V final squared minus V initial squared divided by 2 times mass. If we simplify the formula more, we get the work net equals to mass half mass times V final squared minus half mass times V initial squared. I bet you have seen this formula somewhere before, like half mass V squared minus half mass V I squared. So the half mass V final squared is the kinetic energy of the final, and this is the kinetic energy of initial. So look how easy the formula just got. So V net equals to kinetic energy of final minus kinetic energy of initial. Wow. So this here we have proved to you the work energy principle. So now we're going to be talking about what happens with the work net. Let's say if the kinetic energy of the object increases, kinetic energy of object increases, then the work done is positive. Wow. And if the kinetic energy of object decreases, then work done is negative. And now we have concluded our session here today, and hopefully this clears up a lot of doubts and helps you understand this concept better. Thank you.